Good afternoon. I am Monica Gracida, and this is the class for 5 empirical and molecular formulas. Don't forget to follow us in social media. Okay, this stream is going to be about, we're first going to touch a little bit of base with empirical, ionic and covalent compounds. Then we're going to define empirical and molecular formulas. We are going to describe the relationship between empirical and molecular. We're going to do a little bit of law of definite proportions, present compositions, and then do some examples. Okay, of course you do remember, but what are ionic compounds? Correct? Excellent. Metal and non-metals is correct, and yes, it's actually when when atoms transfer electrons to become ions. Correct. So yes, atoms transferring electrons become ions, and then we have an ionic bond created by electrostatic attraction between usually metals and non-metals. So for example, here on the side, I have an example of a salt, sodium chloride. When we have the formula, in fact, it's called formula units, NaCl, we have the ratio of sodium towards chlorine ions. So it actually, salt exists as a crystal lattice composed of millions and millions of ions of sodium and chloride. The ions will depend actually on the size of the sample. Okay, what are covalent compounds? Correct. Two nonmetals. Two nonmetals that are actually, what are they doing? What are the atoms doing with their electrons to form covalent compounds? Correct. Covalent compounds share their electrons. And just a hint here that will be very useful later. Covalent compound and molecule are synonyms. It's a synonym. So as we know, some examples are water, carbon dioxide, carbon monoxide, methane, glucose, ethene. And something that I want to point here is that, for example, if we have a water molecule, we actually have one atom of oxygen to one atom of hydrogen. In molecules, this is not a ratio, but actually the real formula. We also have more examples as methane, glucose. This is a glucose molecule, right? And ethene with a double bond, but they all exist in that way. I wanted to do emphasis in this difference between ionic and covalent because a water molecule actually exists as one atom and two atoms versus ionic, where they exist as a crystal lattice with millions of atoms involved, well, ions involved. Okay, so now we're going to go next to the definition of an empirical and molecular formula. A molecular formula will be the real one, the real formula of a covalent compound, and the empirical will be the smallest ratio. For example, we have glucose again, and the smallest ratio would be if we divide all the atoms by 6, we will have this ratio. We have ethene, we have water, and yes, sometimes we have the same molecular as empirical formula. This is not, it wouldn't make sense to have empirical and molecular formulas for ionic, because in ionic, it's always the smallest ratio. And it depends on the size of the sample, how many atoms you will have. And in covalent, it does matter because, for example, for glucose, this is the real thing. But we can simplify by doing the smallest ratio. Do we have any questions so far? Okay, I'm going to move on. Okay, Joseph Proust defined the law of definite proportions as the chemical compound will always contain the same elements combined together in the same proportion by mass. For example, he said, water, it's always combined in a ratio of hydrogen to oxygen by 1 to 8 by mass. We can prove this law by doing the calculations of percent composition. Percent composition, it's the mass of an element in the compound over the mass of the compound times 100%. If we do, for example, this calculation for water, we will have that the mass of oxygen in water, 16, does anybody of you know what this 16 represent, or where can we get this value? Correct. That's the atomic mass of oxygen, correct, that you can get in the periodic table. So we'll here oxygen, and then on the denominator, we'll do 2 for hydrogen with the molar mass of hydrogen plus the 1 of 16 to get the total mass of the compound. Then we multiply times 100, and we have 88.8% oxygen in water. We do the same now for hydrogen. And then the addition of the two elements must give 100%. So we can, as we already mentioned with Proust, we can prove the law of percent of proportions with this, and we are proving that water is always a ratio of 1 to 8 by mass, as we can see. 88% is 8 times more than 11%. Okay, we have another example, like if they ask us to find the percent composition of iron in iron 3 oxide, we are going to do the same with the molar mass of iron times 2, because we have 2 atoms of iron in iron oxide, and then do the whole compound below. So we have the amount of iron and the amount of oxygen times 100, and this will be our answer. Can any of you think of how can we self-check if we are on the right track? What can we do to check? We could do the same for the other element. Correct. We do the same for, thank you, Natalie. Yes, Camila. We do the same for oxygen. And then if the addition of the two percentages gives me 100%, this is a very easy way to check if I am doing the correct thing. Okay, so now, how can we use the percent composition to calculate the empirical formula? So this is an example. Suppose that a sample was analyzed and the percent composition was, as shown, 27.29% carbon and 72.71% oxygen. What we are going to do is we can assume that we have a 100-gram sample, and we can change the unit of percent in grams. And then if we do it in grams, then it will be very easy to manage it. We are going to now change the grams to moles. And then since we actually need a ratio, a formula is a ratio, what we do is we divide the moles by the smallest. And then this will be our ratio of 1 to 2. Now we do have the empirical formula. The empirical formula of this sample is 1 unit of carbon per every 2 units of oxygen. Let's do another example. Here we have another example when we have sulfur, nitrogen, and chloride. They're giving us the percentages and also the molar mass of 351 of the molecular formula. When they give you molar mass, assume it's always the molar mass of the molecular, of the real one. So they're asking us, what is the molecular formula? What do we do first? What do we have to assume? Find the molar mass, and we do that. First, we assume that the sample, it's a 100-gram sample, to change the percentage into grams. Then, correct, we use the molar masses of each element to change into moles. And what is the next step? What would be the next step once we have the moles of every element? Correct. we divide by the smallest to get the ratio. So we do divide by the smallest, and we already have the empirical formula. Since the empirical formula is the smallest ratio for the molecular, now we need to find the ratio of the empirical to the molecular. So the molecular molar mass was the given in the problem, and we can easily get the empirical molar mass by using the molar masses of the elements and the ratios that we got on the empirical. Now we divide the molecular by the empirical to get the ratio. Now we know that we multiply the empirical times 3, and now we have the molecular. Okay, we can use this empirical and molecular formula also when we get combustion data from hydrocarbons. Hydrocarbons, they can burn in oxygen to produce which products? If you burn, for example, methane, what products? Correct, water, and what else? You will always produce water when you burn a hydrocarbon, and carbon dioxide. Correct, very good. So if we have any sample of a hydrocarbon, when we burn it with excess oxygen, if we burn it completely, it will form carbon dioxide and water. If it's a simple hydrocarbon, and also if we have a hydrocarbon that also contains oxygen. So we can use, there's ways to analyze combustion products to determine the identity of the original hydrocarbons. So as we mentioned, we burn it in the excess oxygen, and then we have the gases being absorbed by appropriate materials. We will have materials that absorb carbon dioxide and materials that absorb water. By changing the increasing masses, then we can figure out its empirical and molecular formulas. For example, I have an example right here where 17.5 sample of a compound that we know to contain carbon, hydrogen, and oxygen. It's burned in a combustion analysis apparatus. And we have the results of the experiment: 10.5 grams of water, 25.6 grams of carbon dioxide was formed, and the apparatus also can give us the molecular molar mass. So the question is asking, what is the identity of the compound? Okay, so the first thing that we can do, so they're asking us, what is the X, Y, and Z? What are the subscripts of this unknown hydrocarbon? And we have our given. It will be very useful in your AP exam if you place given required in your problems. Teachers love that you organize your work. Okay, so with this information, what can we do? We can assume that all the carbon reacted to form carbon dioxide. So that 25.6 grams of carbon that was given in the apparatus, we can change it to carbon by using the molar mass of carbon dioxide to 1 mole of carbon dioxide to change it to moles. And then we can do the ratio of 1 mole of carbon to 1 mole of carbon dioxide because there's only 1 atom of carbon in carbon dioxide. Then we can use the molar mass of carbon, and then we will have 6 grams of carbon that we got from the combustion apparatus, that we can assume that this amount of grams of carbon came from the sample. Okay, what can we do for hydrogen? If we assume that all the carbon came from the carbon dioxide, correct. We can assume that the hydrogen, all the hydrogen from the sample produced the water. So correct, we are going to do the same. And from the 10.5 grams of water, we can change it to grams of hydrogen, the same as we did before, using the molar mass of water, using the ratio of 2 moles of hydrogen in every mole of water, because we have this subscript here, which represents 2 atoms of hydrogen. And then the molar mass of hydrogen, we have 1.18 grams of hydrogen. What could we do to get the the grams of oxygen of the sample, we already considered the water and the carbon dioxide. How could we get the one of oxygen? Correct. Very good. We are going to subtract the amounts of carbon and hydrogen from the original sample, right? And we are, sorry for, this is not showing correctly, but we can assume that. So what we are doing is 17.5 gram of sample minus the 6.98 of the carbon minus the amount of hydrogen will give us 9.34 grams of oxygen. Now that we already have all the grams of the elements on the sample, what can we do to get the correct? We have to turn it into moles, correct? So we do that by using the molar mass of each element, and then we will have the moles of each element in the sample. What do we do next? Divide by the smallest. Very good. We do divide by the smallest. And now we have the ratio, the simplest ratio, which is the empirical formula. Now that we have the empirical formula, what do we do to get to the molecular? Remember that the empirical is just the lowest ratio of the molecular. And we do have the molecular in the, correct, in the givens. Yes, very good, Cam. So we do use the molecular molar mass, which was given on the original problem. And we use our empirical formula to calculate the empirical molar mass. We do the ratio of both and we get a 3. So that's the number in which we have to multiply the empirical to reach to the molecular. Any questions so far? Okay, let's move on. Oh, well, that was all for my part. I have a question here. Can we only find empirical of covalent? That is correct. This idea of empirical and molecular, it's only valid for covalent, correct? Because in ionic, the formula unit is always the smallest ratio. We don't have this concept of empirical and molecular formula because in the ionic is giving the smallest ratio of the crystal lattice. This concept is only used for covalent. You mean this one's of percent composition? Okay, percent composition, you calculate the mass of every element of the compound by doing the mass of the element of the compound divided by the mass of the whole compound times 100. And then you just use the molar masses of the elements to calculate this. For example, in water, you use the 16 grams that represent oxygen, right, from the periodic table. And then you use the 1.01 for hydrogen times 2, since we have 2 atoms, and 16 grams of oxygen. And that's how you will get the percentage of oxygen. You do the same for hydrogen. Just make sure you have the 100%. Thank you for your attention. Thank you for your attention, and I expect to see you very soon. Bye-bye.